Welcome back, everybody. In this video, we're continuing with section 2.3 with another example. In this one, we're finding the area of a triangle. So a good idea when you're finding an area is to make a sketch of the shape whose area you're trying to find. It says the area of a triangle bounded by the x-axis, the line f of x, which is 12 minus 1/3 x, which is negative 1/3 x plus 12, if that helps you any. And then a line perpendicular to that f, but passing through the origin. So let's work on producing the graph for this. To save us a little bit of time, I've gone ahead and made the XY grid here and labeled everything just to save us a little bit of time. But realistically, you would probably want to find like the important parts here, the x and y intercept, to think about just how to produce your graph. But just to save us a little time, I did this in advance. So the y-intercept, f of 0 is going to be 12. Okay, and then for the x-intercept, we're going to set our f of x equal to 12. Sorry, equal to 0. And then from there, we'll solve by subtracting 12 or adding 1/3 x to both sides. That's easier. And so from there, we can get that x is 36. So the point 36, 0 will be on the graph, and the point 0, 12 will be on the graph. So that will be our two intercepts. So let's go ahead and draw that. We have the point 0, 12 and 36, 0. And then we can go ahead and connect the dots. Okay, next up, it says the triangle is bounded also by the x-axis. So let me go ahead and draw that in just so that we can see it. And then additionally, to the line perpendicular to our f, but passing through the origin. So our original function f has slope negative 1/3. And so ours will have to have a slope that is the negative reciprocal of that. So that will be positive 3. So a line with slope positive 3, and then we need the y-intercept to be 0. Why? Because the line is going to pass through the origin. So it's just the line y equal 3x. So that will pass through the origin, and then we need one other point, okay? So something that's convenient, well, let's try x equal 4. When x equals 4 on this line, the y will equal 12. So our second point will be the point 4, 12. Okay. All right, so there's our triangle. And so make sure that you understand the steps so far. We've basically just drawn a couple of lines when the x-axis was just given to us. We graphed negative 1/3 x plus 12. We found a line that is perpendicular to it and passing through the origin, and drew that graph also. So next, we need to remember that the area formula for a triangle is 1/2 base times height. So the base length on this triangle we know is 36. We just need to figure out the height, okay? For the height will be the y-coordinate, where that came from, the y-coordinate of that point of intersection. Okay, so we need to find the y value where those two lines cross. So let's go ahead and get that next, because that'll give us the height for our triangle. So where those two cross, the line y equals 3x matches the line y equals negative 1/3 x plus 12, right? So where they cross, those two y values will need to be equal to each other. So that 3x equals negative 1/3 x plus 12, where they cross. So now I need to solve this. So to make this easier on us, I'm going to multiply through by 3, which will clear the fractions out. We'll have 9x is equal to minus x plus 36. Adding x to both sides, we'll have 10x equals 36. And so x is 36 over 10, which is 18 over 5. And if you like decimals, that's going to be 3.6. And so taking a look here, it looks kind of like a little before 4. So that seems plausible. We wanted the y coordinate though. So the easiest way to get that is to remember that that point is on the line y equals 3x. And if we figured out that the x coordinate is 18/5, then the y coordinate will be 3 times 18/5. And that is 54/5. 54/5, again, if you like decimals, that's going to be 10.8. Right? And so here my axis scales are such that each box is worth 2. So that's 10. It looks like it's about halfway between 10 and 12. So it's probably just a little shy of 11, which is what we wanted. So the height on this triangle works out to be 54/5. So that was 18/5 and 54/5. All right, so now we have everything we need to finish this one off finally. The area is 1/2 base times height, 1/2. The base length was 36 and our height was 54/5. Okay, so that will be 18 times 54/5. And then you can use a calculator for this. So that looks like about 194.4 square units, whatever the units are. Okay, all right, so then in hindsight, looking back, we were given the situation where we're to find the area of this triangle. It's bounded by the x-axis and then 2 lines that are perpendicular to one another. And the fact that we had the perpendicularity lets us know what the slope on that second line was. The base length was that distance between the origin and the first line's intercept, x-intercept. And then the height of the triangle was given by the point of intersection of our 2 lines. But that does it for this problem. All right, so in this next example, we're using median home values in Indiana and Alabama over a couple of years, or during 2 years, 1950 and 2000. So we have home values in Indiana and Alabama for those 2 times, and they have been adjusted for inflation. So assume that the house values are changing linearly, so we'll take that into account. For the first question, 42, we want to know in which state have home values increased at a higher rate. So it's a 50-year period for both, and so it'll be sufficient to just subtract, right? So for Indiana, it'll be 94,300 minus 37,700. That's 94,300. minus 37,700. So 56,600 in the 50-year period. Just for fun, if we divide through by 50, which was the time period, that is going to be $1,132 per year in Indiana. In Alabama, it'll be that difference, 85,100 minus 27,100, which is 58,000 even. And per year, 1,160. Okay, so to answer the question, in which state were the home values increasing at a higher rate, 1,132 versus 1,160, it looks like higher in Alabama. Okay, in 43, it says if these trends were to continue, what would be the median home value in Indiana in 2010? So this is saying we figured out for Indiana that it's going up by $1,132 per year. We could figure out the whole formula for the equation of a line for this, but I don't think that we need to. We could just think, well, if it's going up $1,132 per year, then from 2000 to 2010, it should just increase by 10 times that 1132. So the value in 2000 was 94,300. And so then we'll just need to add to it 10 years worth of increases, right? So 10 times 1132. So we'll have 94,300 plus 11320, or 105,620. Okay. All right, so there is that. So now, finally, for 44, if we assume the linear trend existed before 1950 and continues after 2000, the two states' median houses will be or were equal in what year? So what we're asked to do here is to figure out some time where the values would be the same. Okay, so Indiana increased from 37 to 94, Alabama 27 to 85 over this time period. Was there a year where the values were the same? So that's what we're after right here. So to do that, we're going to want to figure out the equation of the line for both, and then we'll end up setting them equal to each other, and then, or perhaps using a graph and doing that to form the solution. So give me a minute and I'll put down the equations of the two lines. All right, so what I did was we had already figured out the slopes for each of the two towns. For Indiana, it was $1,132. And so I've got that in there, and then I used the first point, which was at 1950. The value was 37,700. So I put that in for the X and Y coordinates, as you see here, and then went through the algebra to solve for the B, which worked out to be negative 2169700. And then I assembled that into an equation that will tell us, given a year, the value of the home in Indiana. Then we proceeded in a similar way for Alabama. The slope for Alabama, or rate of change for Alabama, was $1,160 per year. And then we knew that in 1950, the median home was $27,100. So I put that in there, in for X and Y respectively, and then algebra to solve for B, and then assembled that all again to give us a formula for the median home value in Alabama as a function of time. So then finally, the question is, we want to know what year would cause these two values to be the same. So essentially, we'll just set these two equal to one another. Sorry, I have my automatic erasing on. All right, so then we need an X in here. All right, so then we just need to solve this equation. So let me do that by subtracting the 1132x from both sides. And then we want to accumulate the constants then on the left side. So let me add the 900 to both sides. Okay, so let's do that. All right, so going through the algebra there, I'm ending up with 2,328. So in a couple of hundred years, the home values will be the same. So fortunately, in the problem, they tell us the answer might be absurd. So I don't know how good our linear model may be going that far into the future. So that's what we got, though. So anyhow, that does it for this example. And we will continue working on section 2.3 in our next video.